Hello everyone, we are going to discuss question number 13 from MTP 3rd. Here it is given that activity of a radioactive sample is decreased to 75%, that is 3/4 of its initial value after 30 days, and we have to find out the half-life. As we know that half-life of a sample can be calculated if we are having the decay constant, as half-life is given as ln2 divided by lambda. In order to calculate lambda, we have to utilize the relation, that is A equals to A naught into e raised power minus lambda t. Here A is the activity after time t, so activity will be 3/4 A naught equals to A naught e raised power minus lambda into t. Here is 30 days, so we will substitute 30. After taking log on both the sides and solving for lambda, we will get lambda is 1/30 ln of 4/3. Now we can easily calculate half-life. As half-life is given as ln2 by lambda, we will substitute the value of lambda and we will get t half is 70 days. So using the fact that we are given, we have to calculate using approximation, the option D will be the correct one. Hello everyone, we are going to discuss question number 15 from MTP 3rd. We have to find out the expression for the linear momentum operator of a particle which is moving in x direction. So let's suppose there's a particle which is moving in x direction. So the wave function for that particle would be given as psi x equals to a into exponential of plus minus iota kx. Here k is given as 2 pi by lambda. So the exact wave function will be given as psi x equals to a into exponential of plus minus 2 pi I x divided by lambda. If we differentiate the term with respect to x, we will get as d psi x by dx equals to plus minus 2 pi I lambda into a exponential of plus minus 2 pi I x by lambda. That term in bracket can be written as psi x. So the ultimate equation will become as d psi x divided by dx equals to plus minus 2 pi iota by lambda into psi x. Now if we divide and multiply by h, so the term will go on like plus minus 2 pi iota by h. In the bracket we will have h by lambda into psi of x. H by lambda can be written as momentum operator. On cross multiplying and solving further, we will get px into psi equals to plus minus h upon 2 pi iota d psi by dx. H upon 2 pi can be written as h cut, so we will get it as plus minus h cut divided by iota d psi by dx. Now removing psi from both sides, we will get momentum operator equals to plus minus h cut upon iota d by dx. Hello everyone, we are going to discuss question number 20 from MTP 3rd. Here a light of wavelength 300 nanometer is made to fall on a potassium surface. For that surface, the work function is given to be 2.26 electron volt, and we have to find out the maximum velocity of ejected electrons. So there exists a relation between the maximum velocity, that means maximum kinetic energy, and the wavelength or frequency. So maximum kinetic energy of the ejected electrons is given as h nu minus phi. Substituting all the given values, we will get the maximum kinetic energy as 3 into 10 raised power minus 19 joule. Now we know that kinetic energy is given as half mv square, so maximum kinetic energy will be given as half m vmax square. Solving for vmax, we will get vmax as under root 2 e by m. Substituting all the values that we have obtained and that are given in the problem itself, we will get the maximum velocity as 8.1 into 10 raised power 5 meter per second. Hello everyone, we are going to discuss question number 35 from MTB3. Here there is a reaction which is provided to us. between 2SO2 and O2 that is in equilibrium with 2SO3. Equilibrium constant for the reaction is also given, and we are told that the initial partial pressures of SO3 and O2 are 1 atm and 2 atms respectively, and we have to calculate the equilibrium pressures of all the species. We will start with writing down the given reaction. Now suppose there is a decrease in partial pressure of SO3 and the decrease is 2x. So the partial pressure of SO3 will be replaced as 1 minus 2x. Partial pressure of oxygen will be 2 plus x, and partial pressure of SO2, which is formed due to decomposition of SO3, is 2x. Now we will apply law of mass action. So Kp will be equal to 1 minus 2x square divided by 2x whole square plus 2 plus x. Now suppose that the decomposition will be up to a low extent, so we can replace 2 plus x as 2 for the simplification of the tedious calculations. So it will become 900 equal to 1 minus 2x whole square divided by 8x square. Now taking square root on both the sides and calculating further, solving it further, we will get the value of x equal to 0.0115. So the partial pressures at equilibrium will be like this. Partial pressure of SO2 is 2x, that is 0.023 atm. Partial pressure of oxygen is 2 plus x, that is 2.0115 atm, and partial pressure of SO3 will be 1 minus 2x, that is 0.977.